Okay, thank you. Welcome back. I think we stopped at loading the lateral soil pressure. We stopped at surcharge effect on the box culvert. Now, what I decided to do before I apply the live load, the traffic loads and the rest, I wanted to demonstrate how you have to work hand in hand with your knowledge and sketches of what you do. We worked on a double cell box culvert. This box culvert has a 4 by 3. Vertical is 4, 3. It has some arches, or these arches. I didn't consider that, but with time you can consider this. You just get the average thickness and you add within this high shear zone. So you have the bottom slab and top slab is given here. The fill is about, the density is assumed to be that, but normally you get that from the geotechnical engineer to give you the density, the angle of friction, the K value, and the rest of it. We have the active coefficient of pressure, which is Ka, which is 1 minus sine theta over 1 plus, which is normally, if you have your phi value of theta as 30, it's about 0.33. Then we also have the passive effect, but normally we don't consider, even for our bridges. We assume worst case that the water has scored or eroded the front field, so you don't need to apply that. So that will be for worst case. Then for at rest is where you do a 0.5 or 0.6. So basically that is, you will have to have all the data. So this is your typical cross section. From the field all the way down, it's about 4.5. But then if you apply your pressure start from up. Then at this point, now you have a surcharge effect at the top of the slab, the box culvert. Then down here, we have that's why you need to know the cross section, and you need to know this one can be given by hydrologists. But when it comes to the length must be given by your highway guy. So when a section is designed, you have the road camber, you have the profile, and then you have gotten where to put the culvert. Then even the angle of repose, all that will help you to shape and come up with the shape of your wing wall. So you can see that actually you have a carriageway about 14, typical. Then you have a 1 meter area where you insert the guide rail, safety guide rails, and then the spread I assume to be 4, but actually you can get proper from the actual site and site condition and the geometry design from highway engineer. You are able to get exactly what you need to handle. I think this thickness is wrongly put. It's not actually. It is supposed to be 4 because you have 500 and 500. I corrected it up here so that you can see the bearing capacity. Normally, gentlemen and ladies, what normally I do personally, when you are doing rock fill, we do excavation, but this excavation you do to remove the topsoil. You just need to get the fact that the foundation for box culvert is like raft. It means it can be sustained at a location, a point where the bearing capacity is at least 50 to 75. So if you can excavate and you have done your DCP testing and the rest, and you are able to know that at this point, maybe 1.5 meter or 2 meters, you have hit soil with bearing capacity exceeding 50. It means now your rock filling can start from there. Because the rock cannot disappear in the soil. So you do your rock fill from that point, bring it up in a well organized, laid properly, rolled properly, to avoid this thing of dumping rock in a clay contents area, which definitely going to distort the compaction effect and other things. So it can continue settling when you're doing, and yet your maximum settlement you are allowing here is about 20, maximum maybe 25. So normally this rock fill, you don't just need to dump it, you need also to be aware so that you guide, and even quantity takeoff, and then even when it comes to audit and you want to check certain things, you are certain that the quantity surveyor is not going to just give you arbitrary volume. You must have a basis to determine your volume. Now, this is now where you look at economy. You're not just going to throw in rockfill or 70 trucks in a place of 2-3 box culvert. But if you calculate and you know the DCP is done and you can accurately determine the profile of bearing capacity within 50 to 75 there, you are good to go. You are good to lay in rocks that the quantities can easily be determined. Right up from the drawing, you don't need to go and say it has disappeared in soil. No. So this is why you see this, I've put this rock and I'm saying BC at least 70 kPa. So basically I'm coming from that direction. Then after the profile here, you need also to know the plan. The plan helps us to know this tapering, the flaring of the apron and the wing walls. You have the shoulders, you have the lane 1, lane 2. This total gives you the carriageway, and they're all given in here. You have a soil of maybe 2 meters, and then the carriage, the lanes are 3.5, 3.5. Now, if you had a bridge, you would have a raise, but now for a box culvert, maybe it's made slightly wider, and then you're able to get a walk through. But for a bridge, normally you have a raised walkway or marked. So down here, I was trying to see how best I can calculate my subgrade reaction. You must have that knowledge. You must have your reference book, textbooks. You have to have the code manuals. You look at all those things, and with the geotechnical information, and you have a good literature around you to be able to come up with what is very, very good. Now, for the lane, when you are dealing with Eurocode, I think there's a formula for Eurocode, but we have now crammed it that for Eurocode you have a standard width of 3 meters. So irrespective of your point where you are measuring from, you do your 3, 3, 3. What remain become a remaining lane. You can do that in a one-way direction, and then you even do your assessment analysis, see the output. Or you put the center line of the deck like I put it here. Then I begin measuring 3 meters going to one side of the cap or right or carriageway, and I have 3, then I have a 2.5. Then this side I have a 3, I have a 2.5. So lane 1 is it. Lane 1 now you measure from your 0 point to the center of that lane, which is the lane 1 is 1.5 on the positive side. Then mean the center line of the remaining lane, which is 2.5, is now you add the 3 plus the half of that, which is 1.25, so give you 4.25 meters. That is what you offset. In the positive direction, you have 2 offsets. Then in the negative direction, since you are measuring your lane from the center of the road, you go leftwise, and you have a negative 1.5 and a negative 4.25. If we had a walkway raised, we would get the center walkway on the positive side and on the negative side. But for this case, I've decided let's do only for the track lane without that. So basically, these are the sketches. You can do as many sketches as possible to help you come up with something that helps you to know what you're doing quickly, and then you're able to enjoy the modeling. So basically, this is exactly what I was trying to. So when you hear someone is saying, yeah, let's assume this, even guys who train you on this webinar, they have done a lot of work in their offices, wherever they have done it. So when they come now to present, they are presenting what now they are exhausted elsewhere. Now for this, I assume that from the outlet. By the way, in reality, this is not leveled. The inlet and outlet has a drop to allow flow, and you know very well gradient for water and gradient for other things if they're solid. And then we also have what they call the cutoff drain. The cutoff beams. Normally we don't show it in the model, but we do a fixed support system to simulate that, because it's down. So normally this cutoff beam, I also personally I consider at least some scoring. You know, there is that eddy currents at the flow and inlet and outlet of culvert. That's why normally you see that the wing will start getting scored, not actually at the front, because of these eddy currents and if there's any obstruction downstream and also at the upstream flow. So there's a lot of scoring here. So leaving it flat, then you are giving room for water to score here and create what they call piping. And then on a serious rain, you'll find that the entire box culvert can be piped. That's why you see a road just falling and dropping down. That means water came and maneuvered outside the boxes. If you don't treat those extent very well, water will maneuver and score all that, and that become creating buoyancy. Actually, now it is flowing full, and it is lifting, pushing while lifting. So you just see the whole road is getting cut off, and it's very hard to explain. Sometimes we say, oh, you see, my road, I designed it, it was attacked by a demon. What was so many things? An engineer begin to talk about demons when actually you have left certain things unattended to. Of course, we do design, but gentlemen, you should also know construction has a lot of things to do. You spend your time designing, then they hand it over to a project manager. You may not be part of the design or supervision team or even review team. Your design can easily be abused. It is even worse during construction. The contractor maybe is not very knowledgeable, and you know the hierarchy in the construction. We do a lot of CAD design, precision, very well done, but sometimes setting out is already given a problem. Quality control, deliberation, those are factors that affect what we do, and so we need to be mindful that sometimes conservativeness. Now the World Road Association has come up with they have seen many things. The trends are not good. Many bridges are collapsing, even during construction. The one that, if it is hit by a ship or a ferry, you find a thing is coming. Because then we were designing for economy. They will say, no, I have this money, let it be this money. So the engineer will struggle if you need. So there were no redundancy. The resilience of the structures have been compromised in a way. There is also now need for climate change adaptability. There's a lot of change in our land use. And so what used to be a deep river now is shallow, and when it is raining, it is becoming, water is spreading everywhere. So what used to be a 20-meter span bridge today, you don't need a 20-meter span bridge. You need a slightly longer to take on the floodplain extent that is coming out because of change in land use. So then extras like this box culvert here, I needed to add one cell to be 3. That means it will take care of climate change. It will take care. It will be resilient. It will be. There's redundancy. At any one point it will never flood because you have taken care of it. But if you make it on this one, and there is a blockage because of trees, because of boulders, like in our western part of Uganda, where we have water flowing from Rwenzori area with boulders, definitely will cause problem. So the World Road Association is trying to work hard. In the next 3 years, you are going to see changes in our design, whereby we are going to begin to look at environment more. We are going to look at the resiliency. We are going to look at the redundancy. We are going back to conservative design. Now, we also have to be careful that anybody can now jump and do design, because conservative means now you over design, but not over design. It has to be well calculated. So even this box culvert we do, even the thicknesses here, you have 300, maybe a 250 could work. Then you'll say, okay, maybe this will happen, problem of ingress carbonation. Let me try to do it 300. Maybe it will give me the robustness I'm looking for. So there's going to be design precision, and then a bit of subjectivity and understanding how the world works, the environment, climate change adaptability, and everything. Then you make some judgment based on now you do expert knowledge versus the theory you have done. So that is exactly what we need to do. So let's pray that what we design is implemented by people who are passionate about what they do and they are knowledgeable with good exposure. So I think this was the explanation. Thank you so much. Now we can go and try to do our traffic loading, and then we do a design. Thank you so much.